So let's, in order to dimensionalize, non-dimensionalize this stuff, let's come up with some non-dimensional quantities that we can then substitute in here. So these are, I guess, pretty straightforward. What we'll say is, if I have a position x, how am I going to non-dimensionalize my position x for some problem? Well, I guess I need to know like a total length scale that I care about. So maybe that would be like flow over a plate, and we'd call that L. So I would say my non-dimensional x, which I'll call x tilde, is going to be defined as x over L. My non-dimensional velocity, u tilde, would be, I guess, u divided by some reference velocity. I guess u infinity would make sense there. What else can we do? For y, so our y coordinate. So then our velocity, v, would be the v component of velocity, which we had been calling v sub delta. We'll just call that v over u infinity. So it's sort of the opposite of the thing I just said, right? This is typically going to be a very small number. Normally, we're going to neglect that in most situations. But we're expressing it with respect to u infinity because we want to prove that we can neglect it. So if that number becomes small, we can throw that away. Yeah?
Because we're trying to get y tilde between 0 and 1, this is only going to be appropriate within the boundary layer.
Yes. Yep, the formulations we're coming up with here are only valid in the boundary layer. OK, so those are the coordinates, velocities. What else can we normalize? For energy, we're going to need to normalize temperature. So let's call normalized temperature theta sub tilde, or theta tilde. And that would be the ratio of the actual temperature at some position x and y minus the surface temperature divided by T infinity minus the surface temperature. So in this situation, I guess we're assuming that T infinity is larger, so this temperature falls between 0 and 1. If it was the other way around, you could flip it if you wanted to. All right, so that's temperature. And then the last thing we need to normalize is pressure. So P tilde would be the actual pressure divided by something. So that something is going to be, again, what is the most that, the largest pressure change that could be experienced by a fluid that's flowing. It's the entire momentum of that fluid. So the momentum of the fluid is rho times u infinity, rho u infinity squared, approximately, right? There's a factor or two in there, but since we're just normalizing it, it doesn't really matter. OK, so this is our set of non-dimensional coordinates and variables. We want to then just go through and substitute these things into this equation, these equations, and get normalized versions. So for the sake of time, what I'm going to do is show you how we do this for the continuity equation, and then I'll just give you the normalized ones for the other ones. OK, so continuity says what? Partial u with respect to x plus partial v with respect to y is equal to 0. So here I need to take u tilde equals u over u infinity, substitute or solve that for u and substitute that in. Down here, this is substitute in x tilde equals x over L, y tilde equals y over L, and this one is v tilde equals v over u infinity. So if I do that, I get partial of u tilde times u infinity over partial of x tilde times L plus the partial of v tilde times u infinity over partial of y tilde times L. With this normalization, what do we have? So you have u infinity over L, u infinity over L. That comes out, and then this is all equal to 0. So those things can go away. right? The u infinities over L go away. And then you're just left with this normalized equation, which is partial u infinity over partial of u over partial of x plus partial of v over partial of y is equal to 0, right? So it's kind of this like simple thing, but we went through the process and we see the resulting equation. The other ones are not as simple because stuff doesn't always completely cancel out because it's not equal to 0. So let me give you the results of the other ones and we'll see maybe something interesting. So if I do the x momentum equation, make my substitutions, I end up with this, which is, just write it out. So u tilde partial u partial x tilde plus v tilde partial u partial y is equal to minus dp infinity tilde partial x plus mu u infinity over L squared L over rho u infinity squared partial squared u partial y squared. That's just making the substitutions. So what is this telling us? Like this is all normalized. These are all dimensionless. But this is this kind of term, right? There's a term here multiplying the last bit. And if you simplify that out, it actually becomes, right, so this actually becomes 1 over the Reynolds number. Right, so this whole thing can be rewritten in terms of the Reynolds number. So that's telling me now if I'm going to develop a correlation, I just need to go through, give me my non-dimensional or non-dimensional coordinates, give me a Reynolds number, and I can evaluate this. So it doesn't need any actual geometry. Just need to plug in the Reynolds number there. Okay, so that's the x momentum energy equation, last one here. If we go through and do this simplification, it becomes, it's a bit longer. So u infinity d theta dx plus v d theta dy is equal to, some of the stuff that kind of comes out of this is k, connectivity times t, infinity minus ts over L squared times L over rho c u infinity t infinity minus ts times all that here, this whole thing here is times partial squared theta with respect to y plus, so I have to go to a new line, plus mu u infinity squared over L squared times L over rho c u infinity t infinity minus t s. And then that last term, all of that is times partial u with respect to y quantity squared. Okay, hand cramps. So, okay, the interesting thing here, non-dimensional term, non-dimensional term. This whole thing is non-dimensional. So this part becomes a non-dimensional group. You know, parameter group, it's non-dimensional. If we go through and further simplify this out, we get on the left-hand side, let's see this one up here. Sorry, I'm 1 minute over. Just give me another 30 seconds here. So on the left-hand side, we have conduction over advection, right, the movement of energy due to bulk mass flow. So this is something called the Peclet number. Peclet number is actually PE is equal to RE times L times the Prandtl number. So that's the non-dimensional group that comes out of that first part. On the second part down here, this is a non-dimensional group called the Eckert number. So E-C-K-E-R-T, Eckert number. And that is defined as U infinity squared over C times T infinity minus Ts. And the Eckert is a relationship between the kinetic energy of the flow due to diffusion across the boundary layer. Right? So it's this kind of movement of energy versus conduction of energy.